Whether it's a combustion engine or an electric motor, it has its optimum efficiency and power range during operation. Knowing how to size a motor to match with your load, such as a propeller, turbine, or vehicle drivetrain, can either enhance the system's performance or its efficiency. In this Part 1 episode of DIY Education Series, we are going to investigate how proper motor sizing and load matching can help to maximize the performance of your mechanical system. When a system's power output is boosted up, it can handle higher load or operate more responsively. To analyze how the mechanical output of an engine or a motor is delivered to a system, we normally look at the power and torque curves. This picture shows the horsepower and torque curves of a typical internal combustion engine. The horsepower curve is depicted by the slope running from the lower left to the upper right corner of the graph, while the torque curve is depicted by the relatively flat curve near the middle of the graph. As the engine speed increases, denoted by the RPM here, both horsepower and torque increase too. But they only increase up to certain engine speeds approaching the maximum, then drop afterwards. For an electric motor, the power and torque curves look quite different. The power curve looks like a parabola and its peak doesn't occur near the speed limit. The torque graph, on the other hand, is more like a straight line, and its peak, called stall torque, occurs when the motor shaft is held to a stop by the load. Upon unloading on the shaft, the motor will start to gain speed and its speed will reach the maximum, called free speed or no load speed, when there is no load added to the motor. Unlike an internal combustion engine, which can't produce torque at 0 RPM, an electric motor can generate torque initially at stop, so it can self-start by itself and doesn't need to maintain at an idle speed during standby. Before we analyze these graphs any further, we should first understand the physical meanings of torque and horsepower. Imagine we have a wheel, and we are going to use a wrench to transform a force applied at the end of it, to create a twisting moment applied to the center of the wheel. This twisting moment is called torque. If we apply a force of 1 Newton at a distance, called moment arm, 1 meter away from the center of the wheel, we will generate a torque of exactly 1 Newton meter. So torque is simply a product of the applied force and the moment arm length. Well, not exactly. Straightly speaking, torque is a cross product of the applied force and the moment arm. Imagine if the force applied to the end of the wrench is not perpendicular to it, the amount of torque will drop. The magnitude of torque is therefore related by the product of the applied force and the moment arm, multiplied by sine theta, which is the mathematical definition of a cross product. To increase the amount of torque produced while keeping the force at constant, the only option is to increase the length of the moment arm, called leverage. Leverage, or mechanical advantage, can be achieved by using a gearbox. A gearbox can either be used to increase the torque or the RPM of the spinning motion. For example, if we have a gearbox whose drive gear has fewer teeth than the driven gear, the torque will be leveraged but the RPM of the driven gear will drop. Vice versa, if the driven gear has fewer teeth than the drive gear, the RPM will be lifted up but the torque will drop. The produced torque eventually reaches the circumference of the wheel, which makes contact with the ground to propel itself forward. Therefore, knowing the amount of torque and the RPM it produces can help us determine how heavy the load the system can handle, or how steep the slope the vehicle can climb. Finding the required torque for a load and matching it to an engine or motor's rated torque is called torque matching, and it is the first step in motor sizing. If the required torque is higher than the rated torque, your engine or motor will be overloaded. If the required torque is much lower than the rated torque, your engine or motor will likely be oversized. Therefore, torque matching is a very important step in mechanical system design. Horsepower, defined as the rate of change of energy, can be expressed as the product of torque multiplied by the rotational speed, RPM. It is how fast the torque is being delivered at a certain time. So horsepower is a direct indication of how fast a system can run with a given force applied. Let's look at the plot here that shows the wheel force delivered by a light-duty vehicle, with a 6-speed manual transmission at various speed and gear ratios. We can use this plot to determine how the engine should be operated, in order to maximize its towing capacity or its need for speed. In the graph, each curve represents a plot of wheel force versus vehicle speed, which closely resembles a typical torque versus RPM plot. Let's put our focus on the plot associated with Gear 4 first. For most light-duty vehicles that occupy a 6-speed transmission, the gear ratio of the fourth gear is close to 1. So this plot depicts how the torque is delivered by the engine naturally without leverage, and we can use this as the baseline. As we downshift the gear ratio increases and the plot gets squeezed. We get higher torque because of the higher gear ratio, but the vehicle speed drops. If we upshift beyond the fourth gear, the gear ratio drops below 1, which means the vehicle is in the overdrive mode. Overdrive allows better fuel consumption at high speed, but there is not much torque for the vehicle to accelerate quickly at such speed. The reason for this is that, when the gear ratio drops below 1, the speed gets leveraged as seen from the horizontally stretched plots. The same engine RPM can now cover a higher speed, but the torque drops as a result. The torque reduction contributes to a weaker wheel force produced, thus makes the vehicle harder to accelerate. Now, let's shift our focus to the dotted line near the bottom of the graph. This line represents the vehicle driving resistance, largely dominated by the air resistance and the tire rolling friction. This driving resistance is the minimum retarding force the vehicle needs to overcome in order to propel itself forward at a constant speed. And this is the force we need to figure out for calculating the required torque and torque matching. The difference between the wheel force curve and the driving resistance curve is the net force available to propel the vehicle. The wider the gap between the two, the harder the vehicle accelerates, and the higher the towing force it generates. So, if we identify the peak of each wheel force curve, we can determine the maximum acceleration and towing capacity for each gear at certain vehicle speed. However, these maxima are good only for identifying the maximum towing capacity and the speed it produces it for a specific gear, but not useful for identifying the shifting point to propel the vehicle to accelerate with the highest rate to reach the top speed. Think of this. If you stick your vehicle in the first gear, for sure you can generate the highest wheel force to accelerate. But as your engine RPM ramps up and the vehicle gains speed, due to the high reduction gear ratio, the vehicle speed will not gain much, even when your engine RPM reaches the red line. In order to increase the vehicle speed further, you have to upshift to the higher gears. You may think that using the peaks of the wheel force curves to upshift may help to accelerate the vehicle at the highest rate to reach the top speed. This is not true most of the time, especially when shifting in higher gears. Imagine if we upshift from the first to the second gear at the peak of the curve of Gear 1. At that vehicle speed, the wheel force will drop from just above 8 kilonewtons to 4.1 kilonewtons. That's a big drop. So the key here is not to just focus on the peak force delivered by the current gear, but also the available force delivered by the next gear up. The goal is to find a point to compromise the two curves. In the case of upshifting from first to second gear, it's still suitable to use the peak of the first gear curve as the shifting point, because the force drops rapidly after the peak on the first gear. But as we look at the higher gears, the same shifting technique may not hold. You can see that the best shifting point for each transition always appears after the peak force occurs. If we use these shifting points to deliver the wheel force to the vehicle can reach the top speed in the shortest time. This is an example of how we maximize the performance of a vehicle powered by a combustion engine. One thing I want to point out specifically in this graph is the point denoted by the red star. This is the equilibrium point where the wheel force produced with the fifth gear is equal to the vehicle driving resistance. At this vehicle speed, the net force is zero, which means the vehicle can no longer accelerate to gain higher speed. So this is the actual speed limit of the vehicle, which is just shy of 200 km per hour. If we define this as the maximum cruising speed of the vehicle, we will use the vehicle driving resistance produced at this speed to match with the torque produced by the engine engaged in this gear. This way, we know we will have just enough torque to produce for the vehicle to operate at such cruise condition. At the same time, when we need extra torque any other time before the top speed is reached, we can simply downshift the gear to generate more torque to accelerate the vehicle. This is an example of how torque matching could be done to a vehicle powered by an internal combustion engine. If you want to know how much power is actually delivered to the vehicle at the maximum speed, you can simply multiply the wheel force by the vehicle speed and you should get around 113 horsepower at the wheels, which is less than what the engine delivers, after the mechanical and thermal losses are taken into account. While the use of multi-speed transmission is essential for internal combustion engines, it is usually not needed for electric motors. The hub motors used for e-bikes, and the induction motors used for Tesla, both don't need gearboxes. And you may ask why? Well, it lies in the fact that electric motors can deliver the maximum torque right from the get-go, but engines can't. If you compare the torque graph between the two, you will see the difference. Internal combustion engines will stall if you apply the full load to it, before it gets to a comfortable rotational speed. That's why a clutch is needed to apply the smooth loading transition. And that's why a gearbox is also needed, to increase the torque from the get-go. Otherwise, the engine will never be able to set anything into motion from a standstill position. In the case of the electric motor, it delivers the maximum torque right at the stall position. So if the motor already has enough torque to do its job in the first place, you don't need a clutch and a gearbox to vary the load, and lift up the torque to get the engine going from stop. This graph tells the difference between the torque delivery of electric motors and that of combustion engines, when the vehicle is set in motion. You can see the torque range of electric motors is a lot wider than the combustion engines, even without the presence of gearboxes. And combustion engines can't generate torque initially at stop. To maximize the performance of a system powered by an electric motor, we will again look at its torque chart to figure out how to conduct torque matching. The motor we use in the example here is a Bain Botz RS 550 brush DC motor. When we look at its performance chart, we should first find out the nominal input voltage used when this chart is produced. We have to know that motor tests are normally conducted when the applied load is varied, while the input voltage is set at a fixed value. Different input voltages yield different torque and power outputs. This figure shows the torque graph at various input voltages. As the voltage incremented from V1 to V7, both produce torque and speed increase accordingly. For the motor we use here, Although the input voltage is not mentioned, we can calculate it from the information provided. Let's pick any point on the chart, say, the peak power. For this particular motor, it generates a peak power of 190 watts, or about a quarter horsepower, which occurs at 9,500 RPM. At this RPM, the motor is running at an efficiency of 37%. Since efficiency is defined as the ratio of output to input power, divide the output power by the efficiency gives us the input power to the motor. Now, you simply divide this input power by the current consumed at 9,500 RPM. You should get an input voltage of about 12 volts. If we define 12 volts as the maximum operating voltage of the motor, and at this voltage, the motor operates at the maximum speed, we can reduce the speed by simply lower down the voltage when needed. After we have defined the maximum operating voltage, we should look at how much torque is required to run the system at our desired maximum speed. Say, if our system requires a minimum torque of 0.35 Nm to operate at the max speed of 5,000 RPM, our current motor configuration will simply not up to the task. There are two reasons behind it. First, there is not enough torque at the max speed we defined, and 2. The required torque is too close to the stall torque. When we vary the speed by changing the input voltage, the motor will stop spinning prematurely when the voltage is dropped to a certain level, because there is not enough torque produced. For instance, a system designed to start spinning at 2 volts may now remain still until 6 volts is reached. I should also mention that we shouldn't run a motor at stall for a prolonged period of time, since the motor coil will get heated up and will eventually burn out. This is the leading cause of a motor failure. We should always give some room to avoid running the motor at the stalled condition. So to solve the problem of not having enough torque at the desired speed, there are two ways to deal with it. First, upsize the motor, or, second, leverage it with a reduction gearbox. Upsizing the motor seems to be an easier way to do, but if it costs more in terms of money and weight, then using a reduction gearbox may be a better option. Say, if we use a gearbox with a reduction gear ratio of 2:1, then the produced torque will be doubled, and the speed will be dropped by half as shown in this new chart here. And all the other curves will be squeezed to cap at the maximum speed of 9,500 RPM. According to this chart, if we want to get 0.3 Nm of torque, the motor will spin at 5,750 RPM when 12 volts is supplied to it. This rotational speed is just above our desired speed of 5,000 RPM. But in reality, since the added gearbox will add some friction loss to the system, you will also expect some reductions in the output power as well as the efficiency. So, the actual RPM may not be far away from our desired one. Even if the actual speed is a bit too high or too low, we can adjust the input voltage to correct the speed according to this chart we saw earlier. Essentially what we are doing is to move the operating point on V7 to a new operating point on V6. In our case, the point on V6 should intersect both the torque at 0.3 Nm and the RPM at 5,000. Then the motor will operate smoothly at steady state. The red line in this graph is similar to the vehicle drive resistance line of the combustion engine we looked at earlier. It defines the required torque we need for our system at each speed. Note that the required torque is higher at the beginning due to the static friction. Once it overcomes that, the required torque drops, but it then gains magnitude when the speed keeps increasing, until the maximum rated speed is reached at 5,750 RPM with a supply voltage of 12 volts. And since our desired operating speed is 5,000 RPM, we drop the supply voltage to a certain value, which will be determined experimentally, until motor spins at a constant rate of 5,000 RPM. The following flow chart summarizes what we have discussed in this video. It may guide you in the decision-making process when it comes to performance optimization in motor, load, matching,